Last week we ended talking about acids. We talked about strong acids and about weak acids. And so now we're going to talk about bases. I'm not going to spend nearly as much time on bases because in many ways it's very similar. The calculations and things are very similar to acids. So again, a strong base. What is a strong base? It's one that dissociates completely in solution. So if we're trying to calculate the hydroxide ion concentration for a strong base, we don't need to do ice tables or equilibrium or anything like that. It is just equal to the concentration of the base, with the one exception that we have to just watch out for. If we have something like strontium hydroxide, where there are 2 moles of hydroxide ion per mole of the base, then we have to multiply by 2. But that's the only tricky thing. So most strong bases are metal hydroxides, and they'll be either group 1 or group 2 metals. And so here's a list of them. You don't need to memorize these. What you need to remember is that a metal hydroxide is a strong base. So metal hydroxides, ionic compounds, when they dissolve, their solubility might be limited, but when they dissolve, they separate completely. So the group 1A metal hydroxides are used a lot because they're highly soluble and we can make concentrated solutions. So when we do acid-base titrations, we usually use sodium hydroxide. And that's because it is very soluble and you can get higher concentrations. The group 2 metal hydroxides are only slightly soluble. So you can only have low concentrations, and they produce 2 moles of hydroxide per mole of the base. So that's something you need to watch out for. Diprotic acids ionize 1 hydrogen at a time. Strong bases do not do that. They just completely dissociate. So you put strontium hydroxide in water, you've got strontium ions and 2 hydroxide ions for each. Weak bases. Weak bases are like weak acids. They do not ionize or dissociate completely. So most of the common weak bases are going to produce hydroxide ions. Remember, that's one of the definitions, by accepting a proton from water. So here we're using the letter B as a generic symbol for a weak base. It's not boron. This is our abbreviation for a weak base. So we put a weak base into water. Bases accept protons. Bases are like the babysitters, right? They'll take the baby and hold it for you. So the base here is going to take one of water's hydrogen ions and become BH+, and then water becomes OH-. And this is why it's a base, because it produces hydroxide ions. So here's an example with a specific weak base. Here's ammonia, NH3. We dissolve that in water. We get ammonium ion and hydroxide ion. Okay, any questions? So like the acid ionization constant, the base ionization constant quantifies the strength of a weak base. So here's our generic base equation. And so Kb is the equilibrium constant for this chemical reaction. So we have the products divided by the reactants. Again, water being a liquid is not included because its concentration doesn't change. If we have a small Kb, that means that the numerator concentrations here, the product concentrations, are small relative to the base concentrations, right? So that means that it is a weak base. It does not ionize very much. A stronger base will have a larger Kb. For something that we say is a strong base, like sodium hydroxide, you can look it up. You won't find a Kb for that because it's essentially infinity. Because a strong base dissociates completely, so you've got products and essentially 0 reactants, and so that goes to infinity. Like we did with Ka, we can also talk about pKb. We talked about pKa, and remember that p is just a function that means negative log of. These are some common weak bases. So if you look at the names of these, a lot of them end in amine or ene. And if we look at their formulas, they've got nitrogen in them, right? So those are the only types of weak bases that I would expect you to recognize that, oh, this might be a base, if it's got nitrogen in it. An organic compound, so we've got carbons and hydrogens and a nitrogen. And in this class, they will always be written with the N and any hydrogens on it at the end. The other two weak bases in here are ions, the carbonate ion and the bicarbonate ion. I prefer to call it hydrogen carbonate ion. So the carbonate ion acts as a base because it can accept a proton from water to form the hydrogen carbonate ion. The hydrogen carbonate ion can also accept a hydrogen ion from water and form carbonic acid. Any questions? So a lot of weak bases are amines. I mentioned that in the previous slide. So we can think of amines as being ammonia with some substitutes. So here we have ammonia, Lewis structure for ammonia. We've got nitrogen with a lone pair, and there are 3 covalent bonds to hydrogen. Ammonia should be familiar. What happens here is this lone pair can accept a hydrogen ion from the water, and we can make NH4+. That produces the hydroxide ion. In an amine, one or more of these hydrogens has been replaced with something else. So you can just detach the hydrogen and stick on this CH3 group. The nitrogen is still going to act as a weak base. We don't need to be able to name this. We don't need to know its formula, but we can do all sorts of things if we know it's Kb. So you'll see it like this, where we have 2 hydrogens on this nitrogen. You might see it where 2 of these are substituted, or even 3 of them have been substituted. And those are all bases. They are related to ammonia. So again, this lone pair takes a hydrogen ion from water, producing hydroxide ion. Any questions? So finding hydroxide ion concentration and pH of basic solutions. So for strong bases, this is relatively simple. We can ignore the autoionization of water and just look at how many hydroxide ions per liter do we have from this base. If we're looking at a weak base, then it's going to be similar to finding hydronium ion and pH of a weak acid solution. Most of the time we can neglect the contribution of the autoionization of water. We're going to make an ice table, and we're going to use the Kb expression to find the hydroxide ion concentration. So here we're going to look at a strong base. The title here kind of gives that away. Doing this calculation, when we look at barium hydroxide, we should recognize that that is a strong base. If you don't recognize it as a strong base and you go looking for a Kb value, you're not going to find one. And that should be your hint that maybe it's not a weak base. So here we're asked to find the hydroxide ion concentration at the pH of this solution. So what we want to do is think of this. If you don't absolutely have to write this down, but you should be able to think about it. So we've got our barium hydroxide, and we're going to put that in water, and that's going to dissociate. And we're going to get barium ions and hydroxide ions. How many hydroxide ions do we get? We get 2, OH2. So that's 2 hydroxide ions. So this concentration that we're given, 0.010, capital M, remember capital M is moles, per liter. Moles of what? Moles of barium hydroxide. We want moles of hydroxide per liter. So you could view this as a stoichiometry problem. I have moles of this, I want moles of that. Right? So I want moles of hydroxide in the numerator, and I want to cancel out my moles of barium hydroxide. And this ratio you can get from the chemical equation. You can also get it from the formula itself, but you have to know to look for that, right? And this is the type of a trick question that I would give you on an exam. I'll give you, I can almost guarantee on the next exam there will be a question where you're asked to calculate something about a strong base, and it won't be something like sodium hydroxide. It'll be something like this where you have to remember to multiply by 2. Okay? So our concentration of hydroxide then is 0.020 moles per liter. Any questions? We do some complicated things in this class, and then when we get to something that's actually really simple, our brains kind of freak out and say, well, it couldn't be that simple. Right? Yeah, some things are, and that's what makes them tricky. Okay, how do we find the pH? Yeah, we need equations, but let's revisit the circle of pH. So, we talked about this last week, the circle of pH. This gives us the relationship between these 4 different quantities. What we have is we have the hydroxide ion concentration, which is down here. What we want is the pH, which is on the opposite side of the circle. You could derive an equation to go straight across the circle, but I think it's just easier to go around. So I don't mess with that. I don't recommend you mess with that either. So we can either go to the right or to the left. Either way will get you the correct answer. Which way should you go? Go the direction that seems easiest to you. I think going through POH is easier because the relationship between pH and POH is very simple. Well, I ran out of space there. You add them together and they equal 14. If we go the other way, we need to use the KW, where hydroxide times hydronium equals 10 to the minus 14, and it's just a little messier. So I always go to the left. So we're going to take hydroxide and convert it to POH. So that's the same pattern as pH. POH is the negative log of hydroxide ion concentration. So the negative log of 0.020. 1.69897. Remember to always write a couple more digits than you think you need. Just, reviewing sig figs here. So our number here, 0.020, how many sig figs does it have? 2. Because the leading zeros don't count, so we got the 2 and the 0, 2 significant figures. When we do a pH or a POH, where are the significant digits? Before the decimal point or after? They are after. So 2 significant figures here is 2 decimal places. I Like I said, I won't try to trick you with that on an exam, but I want you to be aware. Okay, so we've got the POH. Then pH is equal to 14 minus the POH. And that 14 is considered an exact number. So I want 2 decimal places, so 12.30. 2 decimal places is a very common precision for pH and POH. Occasionally you'll see 3, but really not anything more than that. Any questions? Yeah?
Why are you not using the ice table?
That's a good question. Why not use an ice table? Because we don't have to. So, because this is a strong base, it ionizes completely. It dissociates technically. And so there is no equilibrium. Okay? Yeah. And, that's a common thing. I think some people did that last week with the weak acids. We gave you some strong acids on the homework and, calculate these things, and then people are like, but I can't find the Ka, right? Because it's a strong acid, and that's, we're doing ice tables, and then we throw a couple of those in there just to remind you not everything is in equilibrium. Yeah, so great question. Any other questions? Okay, let's do this one. And again, the title kind of gives it away. This is a weak base. Find the hydroxide ion concentration and pH of a 0.33 molar methylamine solution. We don't need to know the formula for methylamine. They give us the Kb, so we can assume it's a weak base from that. Also, if you have something that has amine in the name, it's a relative of ammonia, it's a weak base. So, we do need to write an equation. We're going to have to do an ice table here. Well, I don't know what that formula is. I could look it up, but let's not even bother. Let's just call it B, right? B for weak base. So this is B. Whoops. I have to select a pen to be able to write. So that's just B. So if we put B, a weak base, into water, it's a weak base, so it will be in equilibrium. The base is going to accept a hydrogen ion from the water, which leaves a hydroxide ion. So that's our generic equation for a base, weak base. If you know the formula here, you write that, and then over here, you tack an H plus on it. Okay, so we have to make an ice table. ICE. The water column is not used because it doesn't change. Okay, so we're going to fill in the initial concentrations. What's the initial concentration of our base? 0.33. How about BH plus? 0. How about hydroxide ion? 0. Approximately 0. Now we look at how are these concentrations going to change. Remember, one side of the arrow of this double line, one side is going to increase and the other side is going to decrease. Sometimes it's hard to tell. In this one, it's not hard to tell because this side can only go up. So this is plus x on this side, and that's minus x. With acids and bases, we almost always have coefficients of 1, which makes things much simpler. So then we take our first two rows and add them together. 0.33, I didn't, okay, we're gonna cheat here, steal some space back, minus x, x and x. This seem familiar? Just like the weak acids. I can write the Kb expression for this, BH plus times the hydroxide ion concentration divided by the base concentration. So I'm given Kb. If they don't give it to you, look it up. I recommend looking it up in the textbooks. There's some within the chapter and others in an appendix at the end. Just because if you look on the internet, you might find some slightly different ones or ones at different temperatures, which makes it hard to get that one answer that the computer wants, right? So now we just substitute in here. 4.4 times 10 to the minus 4 is equal to x squared over 0.33 minus x. So the numerator is x times x, so I'm just calling that x squared. Denominator is 0.33 minus x. So we solve for x. We have two options: use the solver or use x is small. So I want you guys to use the solver if you want to, and I'm just going to do x is small. So x is small says that we think this x is so small that subtracting it from 0.33 doesn't make a difference, like losing one peach off of a semi-truckload of peaches doesn't matter. So then what happens is we simplify the math, and so if you write it all out and rearrange it, you end up with 4.4 times, whoops, can't have two decimal places. So x squared would be equal to 4.4 times 10 to the minus 4 times the 0.33. And then to get rid of the square, I take the square root of both sides. So what number did you get from the solver? 0.118. And what was after the 8? 3? Okay. Are those numbers the same? Not exactly, but they're almost the same, right? How many sig figs do we most likely have here? 2, right? If I round this to 2 sig figs, that's 0.012. And if I round the other one to 2 sig figs, it's 0.012. Now, I don't want to round those yet. So, what does X represent? It's the concentration of hydroxide ion. So, using the solver, my answer is going to come out that hydroxide ion concentration, rounded, is 0.012 molar. and using X is small, hydroxide ion concentration is 0.012 more. How do we find the pH? We need to use, I think we should use POH. So POH is the negative log of, well, our concentration. Don't use the rounded value here. Use the extra digits. .9469. pH is 14 minus that. Oops. So pH is 12.05. And if we use X is small, did I do that right? Yeah. So I get 12.08. I thought they were closer together yesterday, but did I mess up something?
Yeah, it is 192. 192.
Pardon me?
Where in the logarithm?
That's a great question. So the logarithm there is because I need to calculate POH. So POH is the negative log of our hydroxide ion concentration. And then I'm going to take the pH and I'm going to subtract the POH. So when I wrote it here, I kind of put those two steps together.
Plus 192. Not 194. The POH.
192. Okay. Yeah, let me check that. 0, 1, 1, 8, 3. Yes. Okay. It's funny. I can't remember what I had for lunch yesterday, but then I look at these numbers and I'm like, wait, that's not the same. Can't remember exactly what it was supposed to be. 927 0. Bless you. Yeah, that looks much better. pHs came out slightly different, but they differ by 1 digit in the uncertain place, right? So not a big deal. What should you do on an exam? You can do either one on an exam. For a multiple choice question, one of these will be listed as the correct answer, and the other will just not be there at all. Okay? Because I'm not out to trick you, except when I tell you I'm trying to trick you, right? And then it really isn't a trick if I warn you about it, is it? No, it isn't. People still feel tricked. So the other answers would be things like 1.93. Because, oh, well, you calculated POH, you forgot to continue and get the pH, right? Or other common mistakes. But if the answer is 12.08 and you come up with 12.07, you should have enough understanding of significant figures to realize that those are essentially the same number. So you pick 12.08. Any questions? So the book's got the X is small approximation because in the test bank, there aren't questions that require a student to use a solver or the quadratic equation because, you know, it's only recently that these things have been so common and easy. You can even, you know, well, whatever. So on the exam, you could always use the X is small. What if you don't like doing X is small? Use a solver, right? You're going to get the same answer or extremely close, and your answer is actually a little better.